All right, so there's two parts to chemical bonding. The first one we're going to talk about is the Lewis model. And these are all theories. And this is actually a really good quote. Theories are nets cast to catch what we call the world, to rationalize, explain, and master it. And we endeavor to make the mesh finer and finer, meaning that you cast out this net and it catches a lot of things, but it misses some of the smaller, finer points. So I guess a great example are the periodic trends on the periodic table. There are a lot of trends that aren't completely explained by effective nuclear charge. We might have to look deeper to find a better explanation or a better theory for that. And so refining that mesh to get more and more complete explanations so that there are fewer and fewer exceptions. Maybe part of what makes chemistry difficult is that the theories themselves, when you get down to it, can get really complicated. And so we say it's easier to learn the basic theory that doesn't catch everything and some exceptions to that, and then we build on that as you take more and more chemistry. So the Lewis model is an example of a model that's not perfect, but gives us a lot of information about molecules rather than just individual bonds. So bonding theories in general give us explanations for how atoms bond together to form molecules and why. So why some would be stable, why others would be not stable or unstable. So you use different models in different areas because there's a trade-off between predictive power and complexity. Lewis models, very simple, very wide predictive power, but at a broad level. So we can use an easier, less complex model. It's not going to have as strong predictive power for every single individual molecule. Or we can come up with crazy computer simulations that do all the quantum mechanics and math, which would be very powerful for a single thing, but all of the data that we need to be able to do that calculation makes it overly complex, depending on what you're trying to do. So here, we're just going to stick with the Lewis model for now and build on that as we go. So Lewis model, we're taking our valence electrons and we're representing them as dots, which is already a gross oversimplification. But it's one that makes sense for Lewis structures and still gives us some decent predictive power. So these Lewis electron dot structures, we just call them Lewis structures, we use them to predict molecules. It's very simple, can tell you about the shape, and can tell you something about the stability of that molecule. So the highest level look at a molecule. So the reason that chemical bonds form is to lower the potential energy between the charged particles that compose atoms, right? Because we've got electrons that are negatively charged, we've got protons in the nucleus, right? The nucleus are positively charged, but we also have some attraction between electrons and nuclei. And so you've got all three of these forces competing against each other when two atoms come into contact. If the result of all three of those forces ends up in a net reduction in energy, that's when you form a bond, because now it's energetically favorable and the nuclei and electron repulsions are less than the attraction between the opposite atoms. That'll actually come up later. So when we're talking about ionic bonds, we'll talk more about bond polarity later, but metals, ionic compounds between metals and nonmetals. Metals have low ionization energies. Remember, that means to lose electrons, so it doesn't take very much energy for them to lose electrons. Nonmetals have negative electron affinities, meaning give off some energy when they gain electrons. In a ionic bond, we've got a transfer of electrons. Metal and nonmetal, those are the ionic bonds. The transfer of electrons. Covalent bonds, on the other hand, are made between two different nonmetals. So rather than giving up any electrons, they each want to gain electrons because they're nonmetals. They want that complete octet. They will instead share electrons. Although, as we'll see later, not always evenly. So again, lowering potential energy, we're able to form a covalent bond, and the electron is the sort of binding force between those two nuclei. Always from the metal to the nonmetal. Yeah, because metals want to lose electrons, nonmetals want to gain electrons. And to put this in a meme format, covalent bonds only share electrons, whereas ionic bonds well, the metal wants to give it up anyway, and the non-metal wants to take it, so it's just like a win-win situation. Metallic bonding, which we're really only going to touch on briefly, is very different from bonding between metals and nonmetals or nonmetals and other nonmetals. It occurs just between two metal ions. So what happens is in nonmetals and in ionic bonds between metals and nonmetals, right, they have ownership over the electrons. One gives up to the other, or they can share them a little bit, but in metals, all of the electrons are shared. And so we actually have this concept of an electron sea. You've got all these metal nuclei close together, freely sharing electrons left and right. And that's what leads to the properties of metals. That's why they can bend, because these electrons, as the book says, the bonds aren't directional, meaning that each metal nucleus would be attached or attracted to the metal nuclei around it equally. So we don't have formal bonds necessarily like we think of with covalent compounds. The metal nuclei in here, they can move around. They can be moved around and they can squish and deform without changing how those electrons are being shared. All right, so we're talking about ionic bonding. Right, if we draw Lewis symbols for potassium and for chlorine, potassium is going to have one valence electron, and chlorine is going to have 1, 2, 3, 4, 5, 6, 7. And again, potassium wants to lose an electron because, as we can see from its electron configuration, it's got this 4s, 1 electron. If it loses that, then it'll have 8 electrons in that previous level, giving it an octet. And we could write out something similar for chlorine. It would be 1s2, 2s2, 2p6. Yeah, 3s2, 3p5. By giving it 1 more electron, we can get Cl minus, which would have 1 more electron, giving it a complete octet. Potassium loses the electron, chlorine gains the electron, and now we've got a positive charge and a negative charge because they just swapped electrons pretty close to each other. So those opposite charges attract and they stick together. Oh yeah, I'm gonna put back brackets. So this is what's always gonna happen for ionic compounds. And we can use Lewis structures to predict the formulas for ionic compounds, just using this basic idea that they're trading electrons. So how many valence electrons does magnesium have? Yeah. The fast way to figure that out, how many valence electrons magnesium has, you look at the periodic table. Oh, I should have my periodic table ready. Periodic table. So for main group elements, the number of valence electrons is the same as the column number, or main group column number. So magnesium's in 2. How many valence electrons does nitrogen have? 5. Yeah, not 15. This would be 5a, so it's 5 valence electrons. So we draw that as 1, 2, 3, 4, 5. So does that correctly predict the formula for magnesium nitride? What's wrong with it? Okay, so if I give up magnesium's electrons to this nitrogen, Mg2 plus, N, is that nitrogen happy? No. It still needs 1 more electron. So again, a lot of the times we draw these as like individual atoms on a page, but you're not going to ever really be able to react a single magnesium with a single nitrogen. So if this nitrogen's floating around and there's also magnesium around, it can steal electrons from another magnesium. So then, let's see. We have Mg2 plus, Mg1 plus, and then N. Is that good? Yay, nay? Huh? Yeah, no, this magnesium's not satisfied. It's got 1 electron that it's still trying to get rid of. So just like pulling in another magnesium, we can pull in another nitrogen. That's an N. M, which has 1, 2, 3, 4, 5 electrons. So that magnesium can give up an electron there. I guess I'm going to, so that would be 2 plus. Now we've got that electron there. Still not good enough. So one more Mg, which brings 2 more electrons, which I can take from it and move over here. Oh, that'll be 3 minus. So then the correct formula predicted by Lewis structures would be Mg3 and 2. Which when we were doing nomenclature stuff, you would have done Mg and said magnesium forms a 2 plus charge, nitrogen forms a 3 minus charge, and you do this crisscross rule, and that'll get you to the same thing. Visualization. So like here, knowing that this is Mg2 plus, we didn't talk about why it's Mg2 plus. Now we've talked about electron configurations and octet rules. So magnesium wants to be Mg2 plus because it's got 2 valence electrons, and it wants to lose those so that it has a complete octet. And same with nitrogen, we didn't talk about why nitrogen forms a 3 minus charge. But now I know nitrogen wants an octet. Gaining 3 more electrons makes it a 3 minus charge. So when you're doing this crisscross rule, really what you're solving for is how many magnesiums do I need to give up enough electrons to satisfy how many nitrogens? And so a total of 6 electrons are being transferred. Yeah. Yeah. It's possible.
Like if it was iron, nitrogen,
Yeah.
then how would you know which kind of iron to get? Iron 2 plus iron.
Yeah, it would be ambiguous. You could do it both ways. You could do the iron 2 plus, or you could do the iron 3 plus. But I think in Chem 2, you look at more why transition metals form certain charges. We don't cover that here. So I wouldn't give you a transition metal plus a non-metal and say write a Lewis structure for this, for that reason. Because it gets a little more dicey. Okay. So we mentioned ionization energies and electron affinities, right? I guess in this previous example, the magnesium wants to get rid of electrons, and that requires some ionization energy, which is endothermic, right? Takes energy to move those electrons away, even though that's more ideal for the magnesium or the sodium in this case. It does take energy to remove those electrons. Then the electron affinity is the energy that's released by chlorine, in this case, gaining that extra electron. So we're transferring an electron from the sodium to the chlorine. When you do this experiment, if you were to react the sodium and the chlorine together, you would get a whole bunch of heat, and it would be very exothermic. But if we look at just the electron affinity and the ionization energy, this is a larger positive number than this is a negative number. So the difference ends up being a positive 146 kilojoules per mole, which means it's endothermic or exothermic. Endo, we're adding energy to it, so it's endothermic. But here, the actual experiment is exothermic. As you may be able to surmise, lattice energy is the rest of that energy, the difference that we're missing. So this is just for the process of taking that electron away from sodium and giving it to chlorine. The thing that's not taken into account is the fact that we've now got a Na plus next to a CO minus. Those are opposite charges. And it's not just one chlorine and one sodium. All of these, chlorines will gather around the sodium on all sides, and sodiums will gather around the chlorines, and you form what's called a lattice. So you've got all of these positive and negative charges that are able to get close to each other, and that's called lattice energy. So those alternating cations and anions getting close to each other releases energy as heat and makes it very exothermic. And it's all because of these potential energies being lowered when opposite charges come together. So it's not because one of them wants to lose an electron and the other one wants to gain an electron. If you do those experiments where you ionize them, ionization energy or electron affinity separately, the energies just don't add up. It's the opposite charges coming together that causes this release of heat. For example, the sodium gas, chlorine gas. Now, so we've already transferred the electron. The lattice energy comes from these all collapsing together into a lattice, being stabilized by the proximity to opposite charges. So what if I took this sodium chloride and I dissolved it in water? Do you think that would be exothermic or endothermic? Why exo? I just said putting them all together releases heat. Yeah, so having them all collapse together into this structure releases heat. The water goes in there and it starts to pull off individual Na plus and individual Cl minus, separating those charges. So dissolving an ionic compound is going to be usually endothermic. Okay, so one way that we can figure out what the lattice energy is with something called the Born-Haber cycle. And this takes advantage of Hess's law. And is also just a hypothetical series of steps representing the formation of an ionic compound from its constituent elements in their standard states. Been a while since we talked about that. But you could do this for Hess's law. So delta H. So we say basically starting with each element in its standard state, how do we combine these together and what energies delta H of formations are those? And does it add up to the overall change in enthalpy? So you have to basically do the experiment where you create sodium chloride, and you have to do the experiments to get the ionization energy and the electron affinity energy for these standard states. But what you end up getting is something that looks like this, which can be very confusing at first. So there's three things going on here. We've got these steps, the 1, 2, 3, 4, and we've got the enthalpy change just for forming sodium chloride from sodium and chlorine in their standard states. And then we've got this formation of the crystalline solid from the gaseous energies, and this is the lattice energy. I'm just going to write it bigger. So the values that you would be able to look up are these ones, and delta H of formation. I guess I should make that a different color because it's... So just to walk through this, essentially we're trying to take sodium and chlorine. These are their standard states. Sodium is a solid, chlorine is a gas. And chlorine not just as a gas, but as a molecular element, so the Cl2. And we need to get those into a form basically so that we have the sodium Na plus and the chlorine by itself, not Cl2, so that they're ready to combine together. Again, those two oppositely charged particles collapsing together to form the sodium chloride, which is why this is the lattice energy. So the first step here is to take the sodium, a solid, and turn it into a gas. And there would be some energy associated with going from a solid to a gas for sodium. And so that would be this change in enthalpy 1. That takes energy, right? Just like boiling water, it's going to take energy to turn it into a gas. So that's energy input into the system. And we would add that to the formation of chlorine atoms from chlorine molecules. So taking this molecule here and splitting it, so now we've just got a single atom. That's again going to take energy because we'll talk more about energies of chemical bonds. But remember, bonds are formed to reduce energy. So if I want to break a bond, I need to use energy to break that bond. So we put more energy in, separate the chlorines. So now I've got a single sodium and a single chlorine. Neither of them has a charge. So now we got to put charges on them. And for ionization energy, removing an electron, it takes energy also, because we're moving that electron, which is a negative charge, away from the nucleus, which is a positive charge. So more energy goes in there, raising us all the way up to this level. Now I've got sodium plus and chlorine, again, no charge. The last step before we can form the lattice is to take an electron and add it to chlorine. And this is the only step that's exothermic in the whole process, aside from the lattice energy. And so that's why this then comes down. And then once you're at this point, the difference between this energy here and the energy here, using just delta H of formation for sodium chloride, is the energy that's released by forming the lattice. So there's essentially a lot of steps. We can account for all of the steps except for forming the lattice. And then we can see the difference in energy has to be from that lattice. Okay. Are there any questions about that? Highly encourage you to go and look at this in the book, read through the explanation, and see if you can make it make sense again later. This is one that you actually had Alex questions on, I think, last week. And we did some examples on it. But for trends in lattice energies, there's really two things that matter. What are the two things that matter? You should know this. Charge and size. Those are the only two things that matter. Are larger charges or smaller charges going to have higher ionization energies? Yeah. 1 plus and 1 minus. So 2 plus versus 2 minus, those charges are more different. So you're going to have a larger difference in energy. So that's going to have a higher ion or lattice energy. And then what about size? It's on the slide. Okay, that is one thing that you could draw from this. It's not the difference in size, but just the size in general. Yeah, lithium and chloride are more different in size than cesium and chlorine, but lithium and fluorine would have an even higher lattice energy. So the closer the ions can get together, the higher the ionization energy. So this is the Coulomb's law. The energy is proportional to 1 over the radius. So smaller radius, or smaller radii, equals higher lattice energy. Because really R here is the distance between the nuclei of the two atoms. Gives more energy. Releases more energy as heat. Yeah, anything. So that's why, so lithium, sodium, potassium, cesium, all in the same column, right? So going down, you get larger. So I could do the same thing if I took lithium and then did chlorine and fluorine. So it'd have a higher lattice energy, yeah. And then going to bromine would be a lower lattice energy. And then going to iodine would be a lower lattice energy. Anything that makes the nuclei able to get closer together is going to be a higher lattice energy. As the ion charge, here we got sodium fluoride, calcium fluoride. They've got approximately the same distance between the nuclei, but calcium and oxygen, 2 plus, 2 minus, those are larger charges. So it's got a higher lattice energy. So lattice energies become less exothermic with increasing ionic radius. And then the lattice energies become more exothermic with increasing magnitude of ionic charge. So larger is less exothermic. Bigger charges is more exothermic. Okay, so we're going to sort lithium bromide, potassium iodide, and calcium oxide. Order of increasing magnitude. So I guess left to right, let's do lowest, highest, what's going to be the lowest or highest between lithium bromide, potassium iodide, and calcium oxide? So lithium bromide, potassium iodide, and calcium oxide. Which one's going to be the lowest ionization energy? Yeah. So we've got two things going on. Again, it's difference in size and difference in charge. So really the calcium oxide, because this is 2 plus and this is 2 minus, it's in a league of its own. And we can't compare it to the, we don't really want to compare sizes with potassium iodide or lithium bromide because the difference in charge is so much greater. And then the lithium bromide is going to be our lowest, or sorry, not our lithium bromide, potassium iodide, because it's the largest and it's only a 1 plus and a 1 minus. Lithium bromide is smaller. Lithium and bromide are both smaller than potassium and iodide, so we would expect that to have a higher ionization energy. And then calcium oxide would have the highest because it's got a larger difference in charge. It's probably also smaller than potassium iodide too, because oxygen's up here and iodine's way down there. You need both. Yeah.
So yeah, so then how would you use size for it? Sorry, I was thinking about size.
Yeah.
How would you able to reduce
The charges?
Yeah.
So the charges for something like calcium and oxygen, you should be able to just figure those out. Right. So you got to think about both of those things. I don't know if it, I guess charges first. Charge is going to make a bigger difference than size. 2 plus, 2 plus 2 minus versus this is a 1 plus 1 minus. Huh? Right. Yeah. You can only compare, I guess that's a good way to put it. You can only compare size. Yeah. So if they have the same charges, then you can differentiate them with size. Sort by charge first. Any other questions on that one?
So why is potassium bigger? Is that because it has more electrons in it?
Yeah, based on where it is relative to lithium on the periodic table. So it's 2 rows down from lithium, so it's going to have 2 more shells of electrons, making it a lot larger. Okay. So Lewis structures, again, so that's like for ionic compounds, it's really just swapping electrons. The metal loses electrons, the non-metal gains electrons, and then we need as many metals and non-metals as to give everything the opportunity to give up all the electrons it wants to give up or gain all the electrons it wants to gain, like the magnesium nitride. In covalent bonds, it's all about sharing electrons with neighboring atoms to obtain octets or duets in the case of hydrogen. And then there are some other exceptions that we'll talk about. So if we do Lewis structures for water, actually we'll go over more formal rules later. Actually, I should do it. Let's do this first. For the simplest Lewis structures, you can almost just at a glance see where the electrons need to be shared. So for water, for example, right, oxygen has 6 valence electrons. Hydrogen has 1 valence electron. Hydrogen wants to get to 2, oxygen wants to get to 8. So it can form a bond with 1 hydrogen on one side, another hydrogen on the other. And now because these electrons in the bond are shared, we can count them for both hydrogen and for oxygen. So for oxygen, it's 2, 4, 6, 8. For chlorine, similar. Each chlorine is short 1 electron from an octet, so they share 1 electron each to form a bond. And then with those shared electrons, now they both can have octets. So if only one bond or one electron is needed to be shared by each atom, you get a single bond. This is also why Cl2, or why chlorine exists as Cl2, the diatomic element, molecular element, because it just needs to share electrons with one other chlorine to have an octet. Same with bromine and fluorine and iodine. For double and triple bonds, so I draw out oxygen. Each oxygen comes with 6 electrons. So it's not enough to just share one set of electrons. You have to share 2. You have to share 1 from each oxygen. And that gives you a double bond. And then for nitrogen, it's a similar thing where each nitrogen is now short 3 electrons. So they each share 3 electrons. And then that forms a triple bond. That's not just something that you need to remember, because I'm going to show you an order to do things for Lewis structures that will help make that more apparent just from the structure itself, rather than having to know how to move these electrons around, because it can get pretty easy to lose electrons. So for molecular compounds, more complicated than ionic compounds, you want to write first the correct skeletal structure. So we need bones for the molecule, so we're going to give it a skeleton. And one thing to remember always is hydrogen atoms are always terminal. Hydrogen atoms are always terminal. Always. They never have more than one bond. I probably don't need to emphasize that as much in this class, because it's Chem 1, but just remember, hydrogen atoms are always terminal. They always go on the end. Then if you have more electronegative atoms, put those in terminal positions. Talk more about electronegativity later. Have we talked about electronegativity yet? Same trend as size, actually. So fluorine is the most electronegative. The least electronegative would be in the opposite corner. So top right of the periodic table is the most electronegative. Bottom left is the least. This is not going to be super, super important yet. And then we want to calculate the total number of electrons for the Lewis structure by summing the valence electrons in the atom. Put it shortly, add up valence electrons. Because when you're drawing out a valence or a Lewis structure for a molecule that's more complicated than just 2 atoms, we're going to do things differently than the way that I did up above, right? Because I drew out hydrogen, I gave each of them 6 valence electrons because that's what they came with. In our molecules, we're not going to do that. We're going to add up all of the valence electrons, and that's basically going to be our bank account of valence electrons. We're going to make withdrawals from that to create bonds, to place lone pairs, to be able to use up all of those. And doing so in the correct order just it'll make your life easier. And this is one of those keys. So now we're going to be distributing all the valence electrons that we added up, and we start to distribute those. So first we want to make, I guess in the skeletal structure I didn't say this, but you got to have at least one bond between each atom and the central atom, or sometimes between other atoms. Be at least one bond. But these remaining electrons, we're going to create octets first. Duets for hydrogen. Basically, hydrogen gets its one bond, and we want to give octets to as many atoms as possible. That doesn't mean like evenly distributing all the electrons around everything, but you start with one terminal atom that's not hydrogen, and you give it 6 more electrons so it has an octet. And then you move on to the next terminal atom, you give it 6 electrons so it gets an octet until you run out of electrons. It does make your life easier. And then, if any atoms lack an octet, that's when you form double or triple bonds as needed to give them octets. I'm going to add here sharing from atoms that already have octets. Whoops.
Right. The atom doesn't have an octet already. Here's electrons. That doesn't help its octet situation. It needs to take electrons from somewhere else through another bond. So
Atoms that already have octets.
basically, skeletal structure, add up the valence electrons, form octets, and then double bonds or triple bonds as necessary.
So the first condition we'll talk about for forming double or triple bonds will be when you don't have enough electrons. Got to include these examples. Oh, I just had to write them in. Okay, so carbon monoxide, skeletal structure, carbon, and I always like to bond in right away. So then the next step is add up the valence electrons. So how many valence electrons does carbon have? 4. And oxygen? 6. And then that'll give us 10.
Now, we use 2 electrons. We formed 1 bond already.
That uses up 2. So we take those out. Now we've got 8. Okay, now where do I start placing those electrons? As lone pairs, but on the carbon or the oxygen? Doesn't really matter in this case. When you do have a choice, start with the most electronegative element. So whatever's closer to fluorine on the periodic table. So if I just
So fluorine than carbon is.
put oxygen first. It doesn't matter. But sometimes it does.
So this is what I mean by giving everything like possible. I start and I just keep giving oxygen electrons until it has an octet.
And then carbon can have it. Okay, so we made the skeleton. We added valence electrons, formed octets.
What's wrong with carbon needs more electrons.
How do I give carbon more electrons? So I'm going to take these. Still not enough. 2, 4, 6. Each bond counts as 2, so we share another pair.
Okay. All right. So,
The central atom.
central?
Give it carbon. Carbon. All right, so we got carbon, we got oxygen, and then
Hydrogens.
and we can. So now we've got oxygen, which is 6 electrons, carbon, which is 4 electrons, and hydrogen, which is really it's 1 times 1 electron each, so that's 12.
How many electrons did I already have?
Made some bonds, so I've got 6 electrons left.
Yeah, on the oxygen first.
Because it's terminal. 2, 4, 6, that's all of them. Now carbon have enough. So now we form a double bond. We can hydrogen, which have 2 electrons, and oxygen's got 2 bonds, 2 lone pairs, which is also 8. So that would be the Lewis structure.
Meaning that it's not at the end of a chain. So it's the last one in a line. It's like carbon here, it's got multiple things that it's attached to. Oxygen's only attached to carbon, so it's the end of the line. The terminal branch. because hydrogen's small. It only needs 2 electrons to have a 2s because it's so having 2 electrons completely fills its 1s orbital. So it's got the same electron configuration as helium, which is stable. But hydrogen or oxygen and carbon, they need more electrons. P orbitals, or partially filled p orbitals. So carbon wants to get up to neon, which is 8. Oxygen wants to get up to neon. And they do that through sharing. So basically, everything beyond hydrogen, or most things beyond hydrogen, want at least 8 as an octet. Talk about that. Great. Chlorine and oxygen. Easy Lewis structure. So hypochlorite. Now we add up the total valence electrons. So how many valence electrons does chlorine have? 7. And oxygen has 6. And we have a negative charge. So this negative charge means that we have 1 more electron. So we add, I'm just going to, our negative charge, we only have 1 negative charge. So for the 2 minus, we'd have 2 electrons, 3 minus, 3 electrons, so on. So total here now of 14. We use 2. So now I can start placing those as lone pairs. Again, forming as many octets as possible. 6, 8, 10, 12. And then because this is, we're told up here that it's charged. So I put brackets around it. Oh, this one? How many bonds? Yeah. 1. 2 electrons. So basically it's saying I've got a total of 14, but I have 1 bond. 2 electrons. Yeah. Okay. No. Not quite. So if you had a 2 minus charge, oh, you have to use the, yeah, this is 1 minus is optional here. You don't throw it in if you need to. It's part of the structure. Change actually changes in a weird way if I don't include it. Basically, it's called a free radical, which in this case, mechanic free radical. That a little bit more formal charges, but yeah. Carbonate. Then we do carbon and oxygen. So this would be 18 electrons. And then another 2. So you got a 2 minus charge. So that would be 24. And I already did 3. So that's 6 out of there. So that's down to 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. And I think it's the next one. Which shares its electron? Yeah. Or a simple Lewis structure, any of them. In reality, this is an example of where you can have a resonance structure. So if I bought here, one of them, shared electrons from my bottom oxygen here, or the one, right? When you're writing out resonance structures, oh, formal charges next. If you're writing out resonance structures, then another resonance structure would be almost the same thing, except sharing with a different oxygen. There's one more resonance structure draw headspace. But first, let's look at formal charges.
Another thing that you can do with Lewis structures is it can actually tell you the charge of a molecule. Or I guess it's better to say we can rationalize why it has this charge based on the Lewis structure. Formal charges. And formal charges are calculated for every atom inside of a Lewis structure. Count it for, in this case, the carbon or each of the oxygens separately. These are made up. So we calculate them, we ignore electronegativity, we ignore the fact that we're partially sharing electrons and how much those are partially shared. But it does give us some explanatory power over why we have certain charges. So we calculate that sort of quickly. The difference between the number of valence electrons and the number of electrons in the structure. So when we do that, we think of it owns all of the non-bonding electrons. So if it has any lone pair, when it comes to bonding electrons, we consider only half of the bond to belong to each atom. I'll draw out the last resonance structure. How about that? So in this structure, if I just look at sort of one of my oxygens, how many oxygens does this have, or how many electrons does this oxygen have in this Lewis? 4, 6, so then it has half of this. When we're talking about formal charge, we're saying like, we assume that all of them are shared evenly. One electron here, one electron. So we say this oxygen has 7. Now, how many electrons did that oxygen bring to the party? 6. So 6 minus 7 equals -1. So the charge on that oxygen would be -1. There's a bunch of different ways to think about this. Instead of it's like memorizing that oxygen is supposed to have 6, or even using the fact that it's got 6 on the periodic table, which is probably the fastest way to do it. The reason that this is a -1 is if I go to the periodic table, oxygen, when it's neutral, it has 8 protons, which means the neutral oxygen would have 8 electrons, right? Now, when I go back to so say it's got 8 electrons, just like neutral oxygen, no charge. So that's 7 valence electrons. Oxygen also has 4 electrons. So if I add the valence electrons that it's got in the structure, 7, if we do, I guess I should say 7 electrons, valence electrons, plus 2 core electrons, that would be a total of 9 electrons. So if oxygen's got 9 electrons in the structure, then it's got 1 more electron and it has protons, and that's where that -1 comes from. The other thing that you can do, especially for like carbon, oxygen, nitrogen, the halogens, we can think of it in terms of how many bonds that they want to have a neutral charge. So let's look at this oxygen, formal charge on this one. So the right oxygen, I've got 2, 4, and then I've got 1 from each of these bonds. So 1, 2, 3, 4, 5, 6. That's a total of 6 valence electrons. If I cut those in half, that's 6 electrons. Well, I guess I should say that's 6. Oxygen brought 6 to the party, minus the 6 that it has in the structure, equals a formal charge. Carbon brought 4 electrons, and it's got 1, 2, 3, 4 electrons from those bonds, so formal charge of 0. So if we look at the periodic table, the halogens always want 1 bond. Oxygen, sulfur want 2 bonds, nitrogen wants 3 bonds, carbon wants 4 bonds. So it's 1, 2, 3, 4. If they ever have that number of bonds, it's 0. Something necessarily to like memorize, but it can calculating formal charges go a little bit faster. Let's actually look at the slides for. Oh, I didn't quite get to the formal charges in a neutral molecule. Add up to 0. the sum of all formal charges in an ion must equal the charge of the ion. Let me redraw this. So we did this one over here, that's a -1. We did the oxygen in the middle, that was 0. Did the oxygen on the right, that was 0. What's the formal charge of the oxygen on the bottom? Also -1, right? It's got the same number of bonds and electrons that the other one had. So that's also a -1. So the charge on this whole molecule was 2-. Way to check, especially for charged ones, for charged molecules, and for neutral ones, right? You can end up with formal charges, but you'll end up with a positive formal charge and a negative formal charge. They can cancel out to give you an overall of 0. Or in a molecule like that. You need a 2-. So you see that 2- charge, at least suggested by the literature, comes from those electrons kind of having more, or those oxygens having more electrons. Now, when it comes to drawing good, you got to follow these first 2 rules. The first rule is that small or 0 formal charges are better than large ones. So let's put that another way. Minimize formal charges. If you have to have formal charges, then negative formal charge should reside on the most electronegative end. So again, closer to fluorine, more electronegative. Okay, it is 6:20, so we will call it there.